Okay, I'm going to take mine out. So we are going to do Newton's method, and hopefully all of you have finished this program. It's like really short. Cosine x is equal to x. But you know, if you want to use the zero finding capability of this machine, then you have to bring everything to one side. You know that much, right? So here at y, I'm just using y. And there are fancier ways to actually have the program prompt you to enter the equation, but I think this is good enough, right? So on y1, cosine x, close parenthesis minus x, and we are going to set that to 0, right? So what we are saying is for what x value is cosine x exactly same as the x itself? Is the question now, isn't it? Yeah, okay. You here now? Okay, then we are going to run this program now. So quit and program Newton. Execute. Okay, bang, x, and then this x1 will be given to you by me tomorrow. So we press 1, and how many? How many should we do? 5, just to see everything on the screen, right? Let's do 5. Boom. Let's compare the answers. Is yours same as mine? Now you notice that comparing the last two, this one is already somewhat correct to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. So this is pretty good. If you keep running it, I mean, these two will improve, but other than that, right? So if you only have to give 6 decimal digits, and this is it. You know what I'm saying? And we got there really fast. You know what I'm saying? Should we? You don't know what I'm saying? Okay, let's run it again. This time, remember these numbers. We're gonna run it like 9 times. Oh, 1, and then 9 times here. You see, these numbers just keep repeating. Once you get to close enough answer, it just repeats itself. So we don't have to run it that far. You know what I'm saying? Okay. Do you ever want to find out the real answer? This is how you do it. Here, right? Graph. Oh, maybe that was not the wise choice. Zoom 6 graph. Yeah, that's what that thing. We are looking for that 0 now, isn't it? So second, calculate 0, left bound, yep, right, yep, and then this computer is just doing, see, that's the number we had. How about that, huh? Okay, so on the quiz, I want this screen. Take a picture of this. Zoom in, so that don't take a picture of all of it. I mean, zoom in as close as you can with your phone. I want this shot. You know what I'm saying? And then I want the shot of your source code program itself, so that I know you really wrote it instead of just somehow created this. You know what I'm saying? Should I have your fingerprint in it just to authenticate? Should we? Oh, wait. Can you hold it up next to your face and take a selfie? Oh yeah, let's do it like that, huh? So that I know you didn't get it from somebody. It's you, really you. It's like that's authentication now, isn't it?
Wait, Mr. Kim?
Yeah.
So are we doing any programming tomorrow or just using the program that we already made to solve problems like this?
Yeah, that's you make the program. Only thing you change is this, right? To whatever problem.
So tomorrow the
Still need
quiz will
to
just be problems like that, right? Use
This is
Newton's
more
method
like
to S.
yeah, this is more like take-home test.
Okay, thank
You
you.
finish the program by tomorrow. I'll give you this, and then you enter it and you make it work. You know what I'm saying? So you might want to test this thing on multiple complex functions tonight. Okay? and make sure, because you know how to graph and do the zero finding thing, then you can compare the answers. You know what I'm saying? Any question on tomorrow's quiz before I talk about differentials now? Okay, then let me assemble my pen and start talking about differentials now. Okay. Yesterday, I briefly talked about it, but suppose we have a graph. And graph of this function, let's say, looks like this. This is our f, okay? Suppose we found the tangent line right about here. Okay, now we want to talk about, well, this is x, right? Or x naught, or whatever, right? And how far is it off? I'm going to exaggerate the picture. This is really almost infinitesimal size. This is x plus delta x now, isn't it? So that much right there is delta x, is what I'm saying. Good? Okay, now, then what is delta y? Well, that's change in y, so this much is delta y, isn't it? Delta x, delta y. So far, so good. Now, but when we say dy over dx is the slope of this blue line. Tangent line is what? Dy over dx. That's a point slope form different, right? Differentiation. So if I change that ratio to be same as this thingy, so if this is dx now, then this is the size of dy. Can you see that in this picture? So, see, originally the limit of delta y over delta x as delta x approaching 0 was the definition of derivative dy over dx. Meaning for small delta x, delta y over delta x is approximately equal to dy over dx. So far so good? This is true for small delta x. It's got to be, because the limit after all is exactly equal to dy over dx, which means that delta y is approximately equal to dy over dx times delta x, eh? This is kind of a profound statement. Okay, or some people like to say delta y is approximately equal to dy. Okay, whichever, that kind of means the same thing, depending on how you interpret this. Now, with that, let's talk about this. See, in science, your science teacher must have taught you by now, no measurement is exact, right? You will never know what exact measurement is, right? Then there must be an error. How do you calculate error in science? You remember this? Is that your error calculation? Okay, this is, if you think about it, this is kind of dumb. This is great for a high school science experiment because you already know what the true measurement is, right? From the back of the science textbook. So you see how far off your answer is compared to that one. I remember when I was in college, one of my project lab was to duplicate Millikan's oil drop experiment. What that was is to measure the charge of an electron. And Dr. Millikan, I think he won Nobel Prize for it, because he's the first guy to measure the smallest possible charge, which is a charge of an electron, right? And then we are supposed to duplicate it. A lot of reading and research went into that one. Anyway, I did it. So then, yeah, then you compare your answer with Dr. Millikan's answer, right? Like this. But if you're Millikan, how the hell do you know what the true is? Because you're the first guy to find it. You see the problem with this kind of error calculation? No, you can't do it like that. Which kind of so your science teacher has taught you to take at least 3 measurements because nothing is exact. If you put a little bit of the element compound on that scale on chemistry class, then that number never stabilizes. It keeps fluctuating and you just need to grab a number and write it down 3 times. You know what I'm saying? Remember that? You still do that, right? Or do you do a virtual lab that on your computer screen, it tells you exactly, this has got to stop, okay? In real life, that chemistry scale is so sensitive. I mean, it's got many decimal digits. It's so sensitive to the air pressure, it'll never stabilize. And you're supposed to just write the answer 3 times and you got 3 different answers. It's amazing, right? Then you don't know which one is the correct one. So how are you supposed to do it? And in real experiment, it's more like 3,000 measurement. If you get 3,000 different data points all disagreeing with each other, how do you know which one is real? You take an average of all, right? And hopefully, if it's not a flawed experiment, this should happen. Should have Gaussian distribution. You know what I'm saying? You know what I'm saying? So if you take an average of the whole thing, that's what we call it. You guys took a little bit of, either you have taken stat or taking stat, or you've done algebra 2, so that you know what this means, right? That's the average, right? It's kind of like your grade distribution. Once you have it, how do you know what your error is? Because we don't know where true is. I mean, hopefully it's right here, but it could be right here. You know what I'm saying? So you have to have some kind of confidence saying plus or minus what? This is election season, right? And they say Biden is leading Trump by 10 points. 10 points plus or minus what? Because last time when they said same thing about Clinton leading Trump by 10 points, they were wrong, right? So it's got to be plus or minus 5 points then, right? It could swing both ways for both candidates. You see how far off these polls could be? It's like, it's definitely good plus. They usually publish it. The scientific ones publish their error. So it's like one candidate, B, is leading candidate T by like 7 points, plus or minus 3. If it's plus or minus 3, is it a realistic lead? No. 7 plus or minus 3, and 3, right? What is it? 0 plus or minus 3. There's an overlap there. You know what I'm saying? Okay, anyway, so do you take, remember, see, if there are 2 of them, then delta y is easy, big one minus small one, right? But you cannot do it here. Do you take this biggest one and then minus smallest one? This is known as the range. That's too big. We don't want to do it that way. So, do you remember what standard deviation is? This picture? This is x plus sigma, and this is x minus sigma. And this contains, what is it, 64%? If you go twice, does that contain 97%? If you go by 3, then it's like 99.5 or something like that, right? So whatever is acceptable in that scientific community, you have to calculate the standard deviation, and then you have to multiply by a certain factor, I think it's 3, and then you publish your answer, right? My measurement is this, plus or minus something. You get it? And the next trick is, So if you use that to calculate something else, right? Because many times you have to multiply, add, formula, plug it into the formula. Then how does the error propagate? You see the problem with that? Is it the biggest possible number minus calculated and smallest possible? No, that gets really too big. So that's our problem. Okay, we measure the radius of sphere to be 6 centimeters plus or minus 2%. Then volume must be something plus or minus what percent? You get it? That's the question. Huh. Okay, so let's do it. Radius is measured to be 6 centimeters plus or minus 2%. And volume is equal to what? Plus or minus what? You get it? Okay. Number one, do you see that this is not a smart question? How the heck do you measure the radius of a sphere? It's not an easy thing to measure. You can measure the diameter of the sphere, and even that's not easy. How do you measure this radius? Radius center is somewhere inside the sphere, so you see that. But for the simplicity of the problem, I wrote it like that. It's usually the diameter or circumference that you measure. Okay, what's the volume formula? What's the volume of a sphere? Oh my God.
Is it 4/3 pi r cubed?
R2.
Okay, somebody substitute 6 and tell me what that is. So your volume is equal to, what is it?
288 pi.
288 pi. Okay, pi, yeah. And plus or minus, right? Now we have to calculate that. That is our question. How does that calculate the error? Do you think it's going to be 2%? No, are you kidding? Don't you wish life is that easy and simple? Right, so how do we calculate this thingy? We calculate dV over my dV over dr, derivative. Is it 4 pi r square? And then dV is equal to 4 pi r squared dr. So far, so good? That much you understand? That's kind of what I wrote here, this thingy. Derivative times that thingy. You know what I'm saying? And my delta r is equal to dr at the moment. What do we plug in where? 4 pi. What do we plug in for r? 6. That's easy. The question is this one. What do we plug in for dr?
2%?
Not quite. It's a 2% of 6. You get it? What's the 2% of 6? We have to actually calculate realistic. So I'm going to push this thing down and have you calculate. So this R is same as 6 plus or minus point what?
0.12.
0.12 centimeter. You understand this? 2% of this is this. So realistically it's off by 0.12 plus or minus. You know what I'm saying? So you put 0.12 here. Do you understand what to do? If you're confused, now is a really good time to let me know. Okay, somebody punch the calculator and tell me what this is in terms of pi.
17.28 pi.
17.28 exactly?
Yeah.
Or, okay. Oh, that's nice. So far so good. So this is 17.28 pi. So far so good. And then cubic centimeters. You understand so far? Now let's calculate the error. Percent error. This is same thing as 288 pi plus or minus. How do we calculate the percent error? Is it 17.28 pi divided by 288 pi? Is that what percent error is? Okay, somebody calculate that and tell me. And you should get, is it 6%? Yeah, well, exactly 6%, huh? That's amazing, huh? Do you understand the whole thing? If you have a question before I move on to just the percent error calculation, let me know right now.
Mr. Kim, for percent error, is there a unit or is it just?
Percent is, let's think about it. This is a cubic centimeter. This is a cubic centimeter, so they cancel. So it's a ratio thing.
Okay, but there are cubic centimeters next to 288 pi.
Yeah, I just wrote it right here. That's why I kind of squeezed it. Because as a scientist, if I write down a measurement without the unit, that's abomination, my God, and I should know better, right? And so should you. Okay, but sometimes, can we just figure out this percent? 6 is so conveniently nice compared to 2. It's just 3 times 2, isn't it? How could we have figured that out? Okay, so I'm going to show you how to do that. Change the colors. So let's come back here. V is equal to 4/3 pi r cubed, and dV is equal to 4 pi r squared dr, right? And let's stare at this thing. Is that our dV over V? Is that how we calculated? dV meaning this is our V and that's our dV, our error. You know what I'm saying? That's how you calculate the percent error. Your error divided by the whole thing. What happens if you just compute that? dV over V. So that would be 4 pi r squared dr over 4/3 pi r cubed. And then you see a lot of things cancel out. Do you get 3 dr over r, or is that too much algebra? Then your only question is, what is dr over r then? Somebody tell me.
2%.
That's 2%. What? Why is that? Oh, let's think about it here. How did we calculate this? We calculate this 0.12 by doing something like this, right? 6 times 2%, right? Do you see it? Then this 2% is 0.12 divided by 6, isn't it? That this is dr and this is r. You get it? Do you get it? You want me to write it down? This thingy right here is dr, and this thingy right here is r, and this is your percent error, isn't it? Do you see percent error is dr over r? Ah, so this thingy is just 3 times 2%. %? Yeah, that's 6%, which is our answer here. Huh. And many times the question itself on the homework and otherwise, they just ask you for percent error, and that's it. And this is you. You notice that we did not need that information 6 centimeter, the radius anywhere. Yeah, and many times it's omitted from the problem. They are telling you to do it this way. Any questions on percent errors? Okay, I'm gonna stop recording.
So the differential just represents the change, like the potential change from the given information, right?
Yeah, that's kind of more like a distribution that I did here. It's like from here to here, it's like, in our case, 2%. So if you have that kind of measurement and that many data, and if you plug it into the formula, you plug this average value into the formula. It's not like you're going to run 3,000 different calculations. You know what I'm saying? You plug this into the formula. This is a 6 centimeter. And then what is the error in volume is what the question is. You see how the science works? Not to scare you or anything like that, but I could just give you a little preview of multivariable calculus. Because many times your variable, it's like you only have one variable here, right? Many times this happens. Right? Your function, whatever it is, it takes multiple input to calculate whatever it is. And you have each like 3,000 measurement for each variable. Now what is the error? And in this case, df xyz is equal to, don't get scared, it's not on your test part. This is known as partial derivative times dx plus times the error and the derivative with respect to z times its error. And this could be abbreviated by del vector times f dot product with delta r vector. Oh no. What? Where this del is partial derivative I vector times j vector, remember ijk? Plus k vector times not on your test, okay? Multivariable. 47. Diameter of a tree is 10 inches. Okay, let me draw that tree, cross section of the tree. That didn't work. Hold on. Let me try that again. Okay, so this is a cross section of the tree. Okay, now it grows, right? So the circumference has increased by 2 inches. Okay, let me draw the new improved tree. Like that. Oh, that didn't work. Hold on. Better? So that it grew by that much. Now, the circumference increased by 2 inches. Then, how much did the diameter increase? Is the question now, isn't it? Okay, what is the relationship between diameter and circumference? Circumference is equal to pi times d. Now, isn't it? So yes. So if we take a derivative, differential, so in other words, dc over dd, although that sounds weird, but dc is equal to pi times dd. That makes sense to you? Okay, now which one do we want? We want dd, don't we? So dd is equal to 1 over pi times dc. Now, okay, my OneNote just crashed. It always happens, I mean, crash happens a lot more when I'm recording. Why is that? This times dc. So far, so good. And that dc is this thingy. So we plug in 2. So this is equal to 2 over pi inches. How about that? That makes sense to you? Okay, 49. We could really, I mean, that you're saying, why are we doing this when we can calculate the diameter difference, right? But no, we are just practicing using differentials here, okay? Okay. side of the square now to calculate the area within 2%. Okay, so let me draw a couple of squares. So let's say there's an error in measurement of the side. Suppose this is the case. Tiny little error, right? So area, and this is S, right? And then A is right here. So area is equal to S squared, eh? And then dA then is equal to 2S ds. So far with me? Okay. And now, how did we calculate percent error? Percent error was dA over A is the percent error, isn't it? So if you do that to the other side, then you have 2S ds over S squared. That gives you 2 times ds over S. With me so far? And what do they want? What they want is the ds, percent error for the measurement of the side now, isn't it? So do you get what I mean by ds over S? This is a percent error. Your error, amount of error divided by the size of the whole thing, ratio. So this thingy is half of dA over A. And that's 2% right here. You get it? So we get 1%. How about that? Question? Okay, I will stop recording. Did it work? Did it stop? Nope.